Hear me okay?
Next up, we have Mike Hasselback, WB2FKO, Synchronization, and FT8.
Hear me okay? All right, everybody. I'm going to start with the ubiquitous disclaimer slide. I'm going to talk about FT8 today, but I'm not an FT8 developer. I didn't help design FT8, and this presentation has not been endorsed or even reviewed by the FT8 developers. That said, I understand part of it, at least I like to think I do, or I wouldn't be up here wasting your time talking about it, and that's the synchronization. So what I did do is work through the Fortran open source code. And yeah, the code is open source, but it's in hundreds of subroutines that represent thousands of lines of code. And I hadn't really looked at Fortran, I'll admit, probably since like 1985. So it was pretty rusty in my mind. So this was hard work. In addition to that, as I went through the code to convince myself I understood what was happening, I took some of it and recast it into Scilab. Scilab is the open source version of MATLAB. There's also one called Octave. And ran some simulations, did some plots, and then finally I attempted to document what I found in terms of the synchronization, and that's what's in the conference proceedings. These are the guys that did design it. I'm sure everyone here is familiar with FT8. It's a submode of WSJT-X, first introduced for testing in June of 2017, a little over 2.5 years ago. Its design was motivated by 6-meter sporadic E, these short but weak openings. FT8 is kind of the go-to mode now for working DX and all the ham bands. And when I say all the ham bands, I do mean even up into VHF, UHF. I was a part of a contest rover, a VHF contest rover last weekend for the September ARRL VHF, and we're working on, I was the digital op, and we worked not only 6 meters, but 2 meters, 222, and even 432, out to like 200, 300 miles. We're making QSOs with FT8 with inaudible signals. It works really, really well. This is the waterfall display, multiple signals coming in through the audio passband of the receiver, time versus frequency. This is from my station on 6 meters, 50 hertz signals and a 2500 hertz receiver passband. This is the GUI, multiple signals decoding. Again, this is summer of 2018 during CQ Worldwide VHF contest, and you can see these multiple simultaneous decodes. FT8 Specs, very, very sensitive, minus 20 dB and a 2500 hertz passband, 8-tone FSK, that's frequency shift keying. These other specs here are very well known. Forward error correction is done with low density parity check code. There was a talk at last year's TAPR conference on this subject. You can find it on Jason's website. I've looked at it twice. I still don't really understand it. But I'm not going to talk about forward error correction here. I'm going to talk about synchronization, which I do think I kind of understand. And that involves this 7x7 Costas array that encompasses about 27% of the total transmit energy is devoted to synchronization. What do we mean by synchronization? Just to get us on the same page here, this is a 6.25 hertz signal that's offset by 40 milliseconds. That's a phase shift. Or we can be offset in frequency, a delta F here of 750 millihertz on 6.25 hertz. So PSK31 and other various digital modes can be set and decoded randomly. However, WSJT, to get this exquisite sensitivity, requires that it provide its own synchronization signal. That's what this Costas array does. So it's got to do things beyond what the typical amateur can do with other sources. So if you, for example, you're trying to synchronize over the internet, it's only going to get you in the ballpark. You've got to go much, much beyond that. Specifically, in the time domain, we've got to be synced, receiver and transmitter have got to be synced to better than 20 milliseconds. And that's accomplished with this 7x7 Costas array. Where did the Costas array come from? It was invented in the 60s for the purpose of dealing with underwater sonar. So you got a ship up there, and he's trying to find the bad guy or possibly the good guy deep under the water. And To figure out the range, this is like in movies like Das Boot, you send out a ping and you time how long it takes to get from your source back, reflect off the target and then back to your source. You can figure out how far away he is. But velocity is a different matter. In velocity, we're looking for a Doppler frequency shift between the on the sending signal. And despite what the weatherman on Action 7 News will tell you, they did not invent Doppler radar. This guy did, or didn't discover the Doppler effect. This guy did. And when I looked this up, I was kind of amazed. This is an Austrian astronomer that was working on this stuff like over 200 years ago. So it's a well-known, long-established scientific principle. However, when you're doing underwater, you've got a big problem. And the problem is that the seawater wipes out your coherence. There's no way to recover any kind of Doppler shift off of this sonar signal due to the dispersion introduced by the seawater. So the solution is not to use a single frequency, but to use this concept of frequency hopping. And so you detect the energy in these various frequency packets at intervals. And as a result, you can recover the Doppler shift incoherently. So this idea of frequency hopping, if you believe the legend anyway, was invented by in World War II by an actress and a musician. And there's a Netflix documentary on the life of Hedy Lamarr, which is pretty interesting. I think it's called Bombshell or something like that. And they developed this for the purpose of trying to confuse jammers on the torpedoes, but the concept here is the same. So to get the idea of the Costas array into perspective, I'm going to go to the spatial domain. So we have a signal reference frame that I've shown here on left in gray, and then the reference frame in black. And we're trying to determine how these things are offset with respect to each other. As so. And the way that we do that is we add some information to the problem, to the frames. So what I'm showing here is a very simple array of 3 yellow LEDs on the left. We put that in the signal. And our reference knows about that and knows where they should be. So what we're going to do is put a stencil or a mask with the same position of those LEDs. So when the signal comes back, we can systematically attempt to max out that transmitted light. We know that we need to have 3 LEDs coming through, so we move around our mask until we maximize that signal. And once we found that maximum, we can then figure out, okay, how much do we have to move it to optimize that transmitted light through? And at that point, we know what delta Y and delta X is. We've established the offset between the reference frame and the signal. What happens if one of the LEDs goes out? This would represent missing information on a communication channel. So I've shown one of the LEDs down in the lower left-hand corner is out. Now when we attempt to align the signal with the reference, we have encountered an ambiguity. There's 2 different ways we can do that. We can put it right on top and we get the two lights through, or we can be offset by 1 integer amount and we get the same amount of brightness. Now we know that one of the lights is out. For sure we know that because our brightness has gone down. We don't know where our orientation is because there's an ambiguity here, a 2-position ambiguity. So how do we solve that? That's what Professor Costas did. He came up with the array that's named after him, where each row and column of our matrix, each row in our column of a matrix has only 1 hole. And I believe the mathematicians call this a permutation matrix, if you believe Wikipedia. So I've shown one of those here, where you've got the hole locations located like this. Now we will get the correct orientation of our reference and signal frames, even if one of the LEDs is out. Now, it turns out there are 6 different permutation matrices in a 3x3 orientation, and 4 of them satisfy the Costas condition. You can see what's happening here is I'm just taking, say, the one in the upper left, and I'm just doing a vertical rotation to get the other orientation. Here, I rotate it along the horizontal axis and then back along on the vertical. So these are the 4 different possible Costas arrays for the 3x3 matrix topology. Now, in a communication channel, we're not interested in positional ambiguity or resolving the positional displacement. We're interested in frequency and time. So we just turn that Costas array into a time-frequency matrix. Now, how does that happen? So when we do that, then we'll be able to determine the frequency and temporal offset. This is what happens in FT8. In FT8, we use a 7x7 Costas array, 200 possible Costas array when you get up to the 7x7 topology, when the array size gets about 7x7. Now, it turns out there's 7 factorial different ways you can arrange these matrix elements to give you a permutation matrix. So 7 different arrangements of 7 factorial, which is like 5,000 something different matrices, and 200, which I thought was an exceedingly large number, satisfy this Costas array criteria. Again, Costas array means that there is a unique distance and angle between each point on the array, which means there's the vector defining the separation between each one of these points is unique. For each pair of data points, there's a unique vector that describes that. And in FT8, that's done with these symbols that are separated by 160 milliseconds and 6.25 hertz in frequency. This is what it looks like. So this is the FSK signal without the audio present. When the operator is running FT8, they pick where they're going to send out their signal in the audio spectrum, anywhere, say, from 200 hertz all the way up to the top end of your receiver, 2,500 hertz, anywhere in there you're going to launch this. I've shown it here without the carrier because you wouldn't be able to see these modulations. But here we're transitioning through just the Costas array, 3, 1, 4, through these various tones to render this in time. Now, in the latest release of WSJT-X that happened in April timeframe, I think, they replaced frequency shift keying with Gaussian frequency shift keying. And there's a subtle difference that I've shown here by blowing up the transition between tone 0 and tone 4, and it smooths it out. And this looks kind of subtle, but it has a pretty profound effect. And that profound effect is illustrated in the next slide here. This is lifted off of a document that you can pull off the WSJT website where they're describing the FT4 protocol, but the idea is pretty evident here. So if you just look at the FT4 spectral waveform, you can see how broad it is, but when they go to the Gaussian frequency shift keying, it dramatically reduces the bandwidth required for this signal. And the real purpose of doing this is you can cram more signals into the audio passband. Don't have to mess with the VFO. You get a whole bunch of signals in there. The narrower the bandwidth, the more you can cram in there. So an FT8 message has 79 time intervals. Each time interval defines a symbol of duration 160 milliseconds, giving a total message duration of 12.64 seconds. 58 of those bins, those symbol bins, are allocated for our payload, which is the message, for error correction, and a cyclical redundancy check. The remaining 21 intervals, or about 27% of the message, is allocated for these synchronization tones. How are these arranged? Well, they're arranged at the beginning, in the middle, and the end. And the span of this signal, again, is 12.64 seconds. So here's the Costas array, shows you where they appear in the various symbol bins through the duration of the entire message. And I'm going to take this. Okay, so the next step, we've got this. How do we decode this? The first thing the decoder is going to do is look for these synchronization signals. If it can't find them, it's going to give up. So that's the first order of business. And it does this in a 2-step process. A coarse search, which is really computationally efficient. It can go through this very, very quickly. And then we do the fine-tuning using this quasi-coherent phase detection, which gets you down to the really fine resolution that the decoder needs. So the first thing we're going to talk about is this coarse search. So this is the waterfall. We have an incoming audio stream. It samples for a full 15 seconds, 12,000 samples per second. You got a 16-bit sound card. You can do the arithmetic. 15 times 12,000 times 16 bits, 2.88 megabits of audio data. And so I'm now taking that waterfall, rotated it by 90 degrees, so now we're looking at it at time. You can see the evolution of the tones. This tone sequence of 3140652, and this is how, it's how they evolve. However, there's multiple streams of data coming in, and they're going to be offset in frequency and also in time. So how do we find these symbols, these frequency symbol bins in the time data? So the data is coming in a temporal waveform, but we really need to be working in the frequency domain. So how do we get from the time domain into the frequency domain? Well, that problem was solved for us a long time ago by this guy, Fourier. This is a recent picture I took off his Facebook page. And the cool thing about it is you can go from the time domain to the spectral domain, but also back again. And this was really hard to do back in the 16th century or 17th century, but the modern computers do this super, super fast. And this is the heart of what's going on in WSJ. They make prolific use of the Fourier transform. So what you do is don't take a Fourier transform of the full time signal. You do these time windowed or time partitioned Fourier transform over the duration only of a single symbol. So we're expecting to see energy, spectral energy in the duration of a symbol, and then we'll take a Fourier transform here and then move by a quarter symbol, 40 milliseconds, then do another one and do another one. So 372 sequential fast Fourier transforms, but interleaved. And so I've shown the first 21 of those 372 at the start of a signal. And this is illustrating how they're overleaved. The vertical axis has no meaning. It's just showing how they're stacked on top of each other. So all these Fourier transforms are saved, and then we're going to try and deal with the spectral information that they produce. So time window, just these slices of the full waveform. So there's many sync signals that may be located in the audio passband. The passband is set by the operator. You can put it on your waterfall. You want to go from where to where. If you've got a 6,000 hertz passband, use the full thing. Most of us have just up to 2,500 hertz. So that passband is scanned in steps of about 3 hertz and also over a 5-second window. So if your PC clock isn't good to within 5 seconds of the other guy, ain't going to work. So if you can get within 5 seconds, WSJT will make up the difference for you. It'll get you synced, provided you're within that 5-second window. So it's going to scan in frequency steps of 3 hertz and time steps of 40 milliseconds. Well, if you do the math, that works out to 126 time steps times 737 frequency steps. If you set the passband from 200 hertz to 2,500 hertz, that's what you get. That's 92,862 separate searches for these costless arrays. And this is what it looks like. Now, your first impression might be that it's some sort of like a new deco art thing, but I'm trying to convey a concept here. We're looking for the energy. And remember, the decoder knows where to expect the energy of those signals. That's a priori given. We know what the pattern of the costless array is. So the red would represent one search pattern. We're essentially carpet bombing the received spectrum. So we're going to look here, 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 and what we're doing is summing up the energy in those bins. Now there's data here, 29 symbol bins. Then that costless array is going to show up again here. Then there's some data, and then another costless array down at the end. And all we're doing is summing up the energy in those bins. Now, if there's just receiver noise there, it's going to record the receiver noise and just add up all these symbols. And here's another pattern, the blue one. So it's looking for the same pattern, but offset with a different time and frequency offsets. And it's remembering all these. It's going to keep all 92,862 of those energy sums in memory. And then it's going to sort them. It's going to sort from the strongest to weakest. And the midpoint of that sort establishes our baseline. So now they've decided that we need to have energy in those patterns greater than 50% above that baseline before we're even going to go any further. If we can't accomplish that, we're just listening to noise. The decoder gives up, okay, we're done. We'll wait for the next 15-second sequence. That's why the time sync is the first line of defense in the decoder. So we're not wasting CPU cycles trying to decode something that isn't there. So you can have as few as 0 candidates or as many as 200. Actually, they've allocated 200 spaces in memory to do further decoding. So assuming we have a candidate that has established this criteria of greater than 50% above the baseline, we have now established the sync of that candidate to within 40 milliseconds and 3.125 hertz. The initial coarse decoding or synchronization of decodings has been accomplished to this level of resolution. Next step, fine synchronization. This uses the concept of correlation, and I'll remind you what that is. What is a correlation? We have two signals. There's actually an animation on Wikipedia or somewhere, or YouTube, that does this quite well. Let's say this is the blue triangle represents our signal. What we're going to do is slide a reference signal, we've got a reference and we've got a signal, and we're going to multiply them together as a function of time, as a function of offset. So when they're offset by, here in the top slide, we get 0, and they're just barely touching here in the next frame, but now they're starting to overlap, and the multiplication is producing a non-zero product, which we're plotting on the right. Then they get on top of each other, and the signal peaks, and then they start sliding past again, and eventually we build up this waveform right here. And the peak of that establishes our overlap. Now, in this particular animation here, the reference and the signal are right on top of each other. But if the signal were happen to be offset by, say, 1 or 2, then the peak wouldn't be there. It would be at 1 or 2. So this helps us to very, very precisely define where the proper overlap is. So the peak of that's the key. The peak of the correlation is going to really help us zoom in and define where the overlap is, and it allows the precise alignment of these two reference frames in time. So how do we do the time correlations in FT8? The energy search is done. We've got all those candidates. We know where they are approximately in frequency. We know approximately where they are in time. So what we do, since we know the approximate carrier frequency, audio carrier frequency, we just yank that off. We baseline it to 0 frequency. Remove the audio carrier. We've got that spectrum. We'll use Fourier to go back into the time domain now. Now we have our time domain signal. We turned our candidate spectrum into a time domain signal. We know where they should be in time, and we can do our cross correlations to get this fine tuning done. So this is what it looks like. Here's what we'd have was a perfectly noise-free signal coming in. This is just the costless array component of the FT8 signal, that 7-symbol sequence. And here's our reference that's generated in the code. And if I do a full correlation of the signal with the reference, I get something that looks like this. And that's a really beautiful peak, super, super sharp, and you're gonna be able to see that to within the resolution of your sampling. The problem is it doesn't work. It doesn't work in practice. And the reason is there's problems. There's physical, real-world problems you have to deal with. Maintaining the phase coherence over the time scale of 1 second when you're propagating over dx distances is not practical. It's just not going to work. Your phase is going to wash out. In addition to that, when I did that simulation on the previous slide, I assumed I knew the phase of the signal in the reference perfectly. So, but we don't know that when we're pulling a signal out of dx land. It could be any possible initial phase between 0 and 2 pi. But more important than that, when I baselined that signal and came back into the time domain, I assumed that the audio, that the baseline signal was known to perfection with respect to the reference. But that's not going to be the case. We only know that to within a few hertz. And a few hertz over 1 second, delta F over a few seconds, can introduce enormous phase shifts. And I've shown here a delta F of 3 hertz. We've swung from 0 to 2 pi 3 times over the duration of the costless array. Now, it doesn't make any sense to you. It's okay. All that we're saying here is I can't do this. That's not going to work. We've got to figure out a better way. And the FT8 developers are very clever, and they did, of course, figure out a better way. And the solution was to do the correlations only over the duration of individual symbols. So instead of doing a 1.12 second correlation over the entire length of this array, we're just going to work symbol by symbol over only 160 milliseconds. So we're hoping to maintain some sort of coherence over the duration of a symbol. In addition to that, when we go from the frequency domain back into the time domain, we can generate a complex number. So we can turn that spectrum into a complex number with a real and imaginary component. So what they do is after they do the correlation, the symbol by symbol correlation, they just work on their real part, and they would just work on the imaginary part, take the result of those, square them, and sum them. And this is nothing more than sine squared plus cosine squared equals 1 that we learned in high school trig. It's one of the really useful tricks with complex numbers. So this is kind of the idea. We're going to correlate symbol number 1, which is tone 3 in the Costas array, with symbol number 3 in the reference. Do that correlation, square it, save it. Do the correlation with the imaginary part, square it, save it, add it together. And you just start summing these things up. So here's the first tone of the Costas array, second tone, third tone, and so forth. Now, what does this look like? We don't have the super nice, sharp, peaked correlation. We get something that looks like this. This is not, as beautiful and sharp as if we did the complete correlation, but you know what? It's good enough. We need to get the time sync to within 20 milliseconds, and this curve is providing it. Of course, the received signals aren't going to have the noise-free characteristics that I've done in the simulation. There's going to be noise present. So what I did is I added some Gaussian white noise to the signal. Here's the real and imaginary part with a signal-to-noise ratio of 2 to 1. Let's take a look at what happens when we have problems or noisy signals. So we're going to take that noisy signal, and again, symbol by symbol correlation. And I should also mention that we're not correlating this whole array. We're just moving. Since we know it already to within 40 milliseconds from our course search, we only have to move these things 40 milliseconds either direction. So it's only 17 time steps. Correlations are CPU intensive, so that's why they save this to the end. The course search is computationally efficient. This takes a lot of CPUs. So they only do this with the candidates that are above the baseline. So we're going to take the signal, the noisy signal, correlate it with the reference, and we get something like this. So the blue is the clean signal, and the black are 3 simulations I ran with random initial phase, Gaussian white noise at a signal-to-noise of 2 to 1, and we still produce very usable peaks. We're still seeing this to within 20 milliseconds. And I do want to remind you that this simulation is only done for 1 Costas array. You're getting 2 more down the road. So there's a lot of opportunity here to find this, even with noise. What happens if we do it with a signal-to-noise of 1 to 1? Now we're really buried in the noise. Well, it turns out you can still pull it out. You can still get a useful correlation peak to within the desired 20 milliseconds. Well, we're not done yet. We got to move to the frequency domain, but the procedure is really the same. We know what our optimum time offset. We just found it. We hit it to within 20 milliseconds. So now what we're going to do is go back and do a correlation, but now we're going to be moving the frequency back and forth in steps of 0.5 hertz, spanning a range of 5 hertz. And again, it's a complex cross-correlation between the signal and reference. Now we're done. We've got our desired time synchronization within 20 milliseconds and 0.5 hertz. So, is it off to the decoder now? Not quite yet. We do one final check. We set the decoder to the optimum delta T and delta F that we just found. Now we take the entire signal and do an additional 79 time-windowed fast Fourier transforms at each expected signal location. And what we do is say, okay, in this particular symbol slot, which one of the 8 FSK tones is maximum? We find that tone and we assign it a number. And we do that for each one of the Costas array locations that we've identified with our syncing operation. Now there's 21 bins, so we could get a maximum of 21 signals that would correspond nicely to our pattern. But it turns out that you only need 7 of them. They have so much confidence in the forward error correction that you only need to have the right energy in 7 of the 21 possible bins to allow it to go to the decoder. Less than 7, it gives up, and it goes on to the next candidate. But that, to me, I found that astonishing, that even with such poor signal-to-noise, if you get 30% of it right in the sync signal, you can still hand it off to the decoder and give it a good try to see if you can pull the signal out. So in summary, the takeaways here, Costas array is a square matrix. A square matrix, a permutation matrix where each row and column has a unique data point. But in addition to that, the Costas array is defined by the fact that each pair of points is separated by a unique vector, distance and angle. And in radio applications, this is rendered as frequency versus time. FT8 uses 3 7x7 Costas arrays at the start, middle, and end. The search is done in 2 steps, a computationally efficient coarse search, and then a fine-tune using this quasi-coherence cross-correlation. Now, I didn't work on this alone. Actually, I pestered the developers quite a bit, and pestered is the right word. They patiently answered my questions until I started feeling that I was becoming a pest. But Steve Frank was very helpful through this process. The Fortran code is largely uncommented. Maybe once every now and then I would see a comment. So this was a struggle, and they helped me through it. I got interested in this pretty much right after the TAPR conference in Albuquerque, talking to Phil Karn. I don't know if he's here, but yeah, right there. He kind of got me motivated. And Jim Frazier gave a talk on FT8 at the Albuquerque TAPR conference last year, and that, I've been working on it on and off pretty much ever since. And you know what? That's about all I have to say. Thanks very much.
Do we have some questions? Oops, I'm sorry. Any questions? Okay, over here. And Phil.
So I'm not an FT8 user, so forgive this really stupid question. And this probably has something to do with the timing. But is the decoder capturing the entire 14 or 15 second segment before it tries to do any of this?
It's not decoding in real time. It takes, depending on how fast your CPU is, it waits till the whole thing is done, and then it goes off and does its thing.
Okay,
There's
so
another mode of WSJTX called MSK144 that's used for meteor scatter, which does decode in real time, or quasi-real time.
Okay, so I think that answers the... It's working, is it? All right, I lost my train of thought. Okay, so I think that might answer my question, because if it's got these 3 matrices it's trying to match up, they all look identical. How does it know it's not starting in the middle?
That would be too far off.
It would be because of the timing.
Yep.
Okay. Right.
And that's actually a good question. FT4, which is the new contest mode that came out, uses 4 Costas arrays, all different. And I wish I could tell you why that's the case. I'm not an FT8, FT4 developer. You'd have to ask the developers.
Yeah, more of a comment, really. First, I'm always fascinated by the fact this coding is so strong that I can turn my transmitter halfway through an interval and still be understood if the signal is strong enough.
Yeah, I'm not sure I believe you on that.
That's true. Well, maybe not halfway.
Yeah, because there's information in the
instant.
Close to half, maybe 60, 70%.
Yeah, and a point also I think I pointed out to an email when we were talking about this is that the whole point of everything you talked about here is just to tell you to go ahead and attempt to decode on the data part of the packet. And sometimes I wonder if it's really necessary. Why not just, in some of the schemes I've designed, I don't put in any synchronization at all. I just try all possible offsets until something falls out.
I thought about that, and again, I'm not a developer, but I think I have an idea, and that's because this is strictly speculation. There are people that are copying the code, and I do know that between version 1.9 and 2.0, when they went from 72 bits to 77 bits, they ended up flipping the Costas array 180. So the sequence got completely reversed. And I think they don't want other folks attempting, they see all these waterfalls coming in, they're running the code, and the waterfall's going to display it, but there's nothing decoding. They don't want the program to go through, showing a flashing light, I'm attempting to decode, nothing's decoding. They just want it to give up. So I think it's the idea to make it just so incongruous with old versions and other folks, and they want you to stay on the bleeding edge.
That wasn't really my point. The point is you could design a system like this with less synchronization because it takes so little time to attempt to decode anyway with modern CPUs that are so fast. When I see it, I mean, it's taking
Yeah, okay, I
very little on my
understand.
CPU. You don't really have to go through a lot of this because all this, the purpose of all this is to save CPU.
Okay, I
in the
understand your
decode
point.
attempt.
Yeah.
And they're
yeah.
not using much anyway. That's all.
Thanks. Any other questions? Thank you very much.
one there.
Oh, I'm sorry, Steve. Yeah, everybody hold their applause.
I was a little curious if you had any comments on the coding. Just sitting here thinking about it, I would expect that occasionally the message pattern would match the COSTUS bits, and you'd have trouble with that because it would misalign on the synchronization. Is there coding that avoids that?
I get that question almost every time I give this talk. Yeah. The only thing I can tell you is that they probably configured their LDPC matrix to not produce that. Yeah. I don't know. I can't answer that. But it's a great question I've thought about a lot.
Okay. Thank you very much.